Okay, so you're copping down this title, and what I want you to start with is filling out these. After doing that learning goal, hopefully you know them. Those two are basic. We better know those ones, otherwise we're in trouble. What about these ones? Do you know these ones? So just try. Make a guess. I've probably mentioned this before. It is useful. Some people are so hesitant. They don't want to make a mistake. Well, this is the lesson. I want it to be perfect. No, like you gotta put yourself out there. You gotta take a risk. I'm not really sure what that is, but I'm gonna kind of like shot in the dark guesses. Sort of remember what we did yesterday, and then see if you're right, or if you're close, or if you're way off. That's a valuable thing to do and then reflect on. We don't do enough of that. That's like fear of taking risks. We're too nervous to take a risk. Well, I don't want to do it because I might be wrong. How are you ever going to learn? Okay, first one's easy. Somebody give me sine. Derivative of sine. Good. Thank you for doing it the whole thing as well properly. That's perfect. Cos u times u prime. And derivative of cos? Good. Does anybody remember tan? Good. And then cotangent hasn't really come up, but very good. Another thing that's interesting about these little moments where you're given an opportunity to sort of try something like that, studies have shown that your memory improves with practice. Maybe that seems obvious, I don't know, but this is kind of a new or a newer-ish thing where what it means is like, if you try to use your memory, it'll get better. And sometimes we don't, we just look things up too much instead of trying to remember it ourselves. And even if you try and you can't, I think that helps for the next time. You know what I mean? So it's good to just throw it out there and try once in a while. Okay, we're not doing this today. We're going to do a day on derivatives of other trig functions like cotangent, secant, and cosecant, but we're not doing that today. But I thought it would be fun to see, given what we did yesterday, can you figure out what the derivative of this is? So see if you can do it. So if you're not sure, what we did yesterday is we took something that we didn't know anything about and we turned it into something that we do know something about, right? So when you, like, we can't take the derivative of something that we have no idea what the derivative is. But what is secant related to that we do know something about?
1 over cosine.
It's 1 over cosine. So we would switch it to that, right? Good. And another little tip is if you're in new territory, it's good to rewrite things into familiar, like a more familiar way, an easier way, so you're really looking at what it actually is. So I would even go so far as to rewrite this as cos x to the -1. Interesting aside, important to point out, I think. What if I wrote this as cos -1 of x? Same thing? Like cos x all squared is cos squared x. So I suppose you could do this, but what's weird about that? It looks like inverse cos the way it shows it on a calculator. That's how they show this. The -1 is also, unfortunately, a symbol for inverse in mathematics. It's a terrible mistake that was made a long time ago. And unfortunately, both of those standards are just so built into our mathematical system now and the notation that it's kind of like we're stuck with them. People have tried, even in the last, 50 or 100 years, to offer, like, can we please change this notation? Like, let's use this instead. But it just doesn't take, right? Because it's really hard to change notations that are embedded deeply in a culture. So, unfortunately, this looks like inverse cos, like shift cos. So we don't typically use that. In this case, I would write it like this, just to be aware of that. But if you did write it the other way, it wouldn't necessarily be wrong. Now, when I take the derivative of this, be careful. So remember, we do, and this was my advice yesterday, say it to yourself in your head. Exponent, trig, angle. Exponent is -1. Cos x. Subtract 1 from the exponent to the -2. Times the trig part. Derivative of cos is -sine. And then the derivative of the angle is just 1 in this case. So we don't need to worry about it. Okay, so if you got that far, that's fantastic. How can we clean this up? Well, I can take the negative and the negative and get rid of them. I've got a sine x on top and a cos squared x on bottom. And this works out too. And like, this is where it's not about rules. It's not about, it's obvious that you would do this. I'm going to show you the standard way that we would usually write the derivative of secant. Excuse me. But maybe you want things in terms of sine and cos, and you would leave it like this. Kind of like yesterday, it totally depends on what you're doing. So this is going to be 1 over cos x times sine x over cos x. Yes? No. Yeah. Like, you mean right in the denominator here? Yeah, not wrong. And what is this? This is secant. And what is this? This is tan. So that's kind of a nice clean way of writing it as well. The question was in terms of secant, so maybe we want to leave the answer in terms of secant. Like, that might be a thing. It totally depends on context. And not what we're getting into in this course. We're not going to be doing enough of this that we're really going to worry about those kinds of things. I'm going to go back up here and write it down. We're not even doing this today. We will do derivatives of things like secant later. But we'll write it down for now just so we have it. So that was secant u times tan u. And then it would be times all of that times u prime. And what about another guess? What do you think cosecant would be? So I want you to look at all of the other 5, look for all the different patterns, and wild guess. What do you think it might be? You don't have to get right, even if you get part of it, that'd be great. Cosine? Okay, close, not quite. Somebody want to? Negative cosecant. Good. What do you think's next? Very good. It is cotangent. And then times u prime. So notice that like cotangent goes with cosecant and they're negative. Cosecant and cotangent, they're negative. Tan and secant go together in both cases. Like there's patterns here, right? So, once you kind of get that, it's hopefully not too bad to memorize these. These won't come up too much. But we're going to do a day on them. All right, now let's try a few more. Again, I want you to give these ones a shot. This one, some of these are just more practice. Some of these have little quirks that we just want to be aware of. Common mistakes that might happen. What is this one actually saying? Because there's two ways that this gets interpreted, the right way and the wrong way, but what do you think? Isn't this like sine of x to the 1/2? Some people might interpret this as sine x all to the 1/2. But that one's wrong. This one's right. Okay? Because it's just the square root of x. Otherwise, it would be like square root of the whole thing. That would be an exponent like this. Okay, so give that one a try. So I got that as my first step. Derivative of sine is cosine. So sine of root x is cos of root x times the derivative of the angle. And then we can clean this up a little bit. When in doubt, use brackets. If you're not sure, you can put brackets around your angles like that just to make sure that you know where the angle stops. But generally speaking, if I don't have brackets, it just stops after the first thing. If it's adding, for sure it stops. Even multiplying, this would be cos x times all of that. So this ends up being cos root x over 2 root x. Sound good? Okay, try that one. What do I have to be aware of for this one? Quotient. Very good. So hopefully you got something like this as your first step. Derivative of the top, which is just 1 times the bottom, minus the derivative of the bottom. Derivative of tan is secant squared times the top over the bottom squared. Now listen, I'm going to say this over and over and over again because I know that it's something that's on people's minds. What if this question was find the equation of a tangent x equals pi. Well, you could just sub in here and do it, right? You could just figure it out at this stage. So is there any value to simplifying this? It depends on how many steps. If you can do a nice simplification in 1 or 2 quick steps that you see already, sure, go for it. But if it's going to take you 5 or 6 steps to turn this into something that's a marginally easier, I don't know why you would do that. So there's no trick, there's no answer to that you have to. You could absolutely sub in and solve here. This should be to find the slope, if it was that kind of a question. If this was a question, just take the derivative, you would be done here. You wouldn't be required to simplify because it might or it might not, right? That being said, we've done a lot of work with identities, and this is where that work starts to come in. If you're a mathematician or a student or even, and you're breaking new ground, like you're exploring something new, it's like doing identities, except you don't have the answer that you're working towards. You don't know what you're trying to make it look like. But all those steps, all those skills that we built in taking the left side or the right side of an identity and manipulating it to simplify things and looking ahead, well, what might happen? What if I did this? Oh, that would happen. What if I did this? That would happen. That does come into play here, right? So those skills are useful. So you might do something like this. So we're going to play around with it a little bit, but again, I can't think of a time in this course where you would be required to do something like this, or you would have to know when you can and when you can't. But in this case, I would probably split the numerator into 2 fractions, and I would get tan x over tan squared x minus x secant squared x over tan squared x. And the first part is like x over x squared, tan x over tan x squared. So this is 1 over tan x. And this is minus x times, and I'm going to change secant squared to 1 over cos squared, because in identities we often change everything to sine and cos. That's a thing. And tan squared is sine squared over cosine squared. But it's in the denominator, so I'm going to flip it. And this is a really good example of one that cleans up quite a lot, because now I've got my cos squareds divide, and they're gone. And I can write 1 over tan x as cotan x minus x, and 1 over sine squared x is cosecant squared x. So that tidied up a little bit nicely. Again, if you were solving this to find a slope, we would probably leave it as tan and sine, because that's how we solve those. Like, how do we solve when it's a reciprocal? We switch it back. So it all depends on the context of what you're doing. But this is just a demonstration of what you might be able to do. And if you're really good at identities, you might be able to spot that quickly, that it's going to tidy up nicely. I don't know. Okay? So keep that in mind. And again, I think I said this yesterday, some of the questions in the homework throughout this unit, the answers require a bit of manipulation, I think. So I don't know. Try this one. It's pretty straightforward. That dot there indicates pretty clearly what you have to do, but sometimes the dot's missing. But the dot means obviously this is going to be product rule. Okay. So go ahead and give it a shot. So the derivative of the first thing, x is just 1, times the second thing, sine 4x, plus the derivative of the second thing, which is here in green. And I did the trig function first. Derivative of sine is cosine. Don't change the angle. Then times the derivative of what's inside the angle, the derivative of the angle. And then times the first thing. And again, generally speaking, just like back in Unit 2 of this course, we would typically tidy up monomials and maybe get rid of negative exponents, that kind of thing. But that's about all that we would do. Unless there's something else you could do, but in this case, I don't think there is. Questions, everybody okay? A couple more of these. Let me try that one. What is good to note about this one?
Cos pi by 4 is a constant.
Very nice. Cos of pi by 4 is a constant. So it's best if you, constant. It's best if you notice that right away. Now, if you didn't, you might do something like this. Oh, well, the derivative of cos is negative sine, so this is going to be negative sine of pi by 4 times the derivative of the angle, but the derivative of that is 0. So you just get 0 anyway. So does this work? Yeah, I guess, but it was kind of a waste of our time. Cos of pi by 4 is 1 over root 2, like that's a number, right? It's just constant. And then we have product rule. Sine squared 3x is one of those ones that's got all three parts. Exponent first. Subtract 1 from the exponent, 2 goes down to 1. Then the trig part. And the derivative of sine is cosine. So times cosine of 3x. Then times the derivative of the angle, which is just 3. You okay with this? Factor out a negative 4. And in fact, I've got a sine 3x and a sine 3x, so I can factor out a sine 3x. And then I'm left with, I think, sine 3x plus 2 times 3 is 6 cos 3x. This is a trick we've seen a few times, but maybe not enough times. Maybe not everybody's seen it. I could also have, so it's 0. I can factor out the negative 4 here. If you go back to the Unit 2, this is constant multiple rule. I could factor out the negative 4 and then take the derivative of what's left, which is x times sine squared 3x. It just gets factored out in the end anyway. So you're going to end up with the same thing. Maybe that's easier. Some people like that kind of thing, so point that out. It would end up being the derivative of the first thing, which is just 1, times the second thing. So it ended up being sine squared 3x. But then plus x times 2 sine 3x times cos 3x times 3. Ends up being the same thing. Okay, last one like this, and we're going to do one more. This one's got everything, so it's just another good practice. Got all 3 parts. Give it a try. Say it in your head. Exponent, trig, angle. So the blue is the exponent part. Green is the trig part. Orange is the angle part. Only thing I could possibly do is bring that negative sign out. And maybe it would be a little bit nicer to write that first, but really there's nothing we can do with this one, and that's not the point of this kind of a question. There will be a question like this, I'm sure, on the quiz. And you're typically required to tidy up monomials, but that's about it. Any questions about that? Common mistake or common question that people have is, if this is cos cubed, why is this sine to the 1? And the answer is, think about this. This is like cos of x squared plus 3x minus 9 all to the 4. So when I take the derivative, the 4 comes out. I get cos of that same thing times 3. Or sorry, to the 3, not times 3. Just like if I was doing 2x cubed minus 4x to the 4. I bring the 4 down, and I get 2x cubed minus 4x to the 3. But then I just multiply by the derivative of what's inside here. Not this to the 3, just this, which would be 6x squared minus 4. So think about it like this if you have to, about why that sign is to the 1. Because it is. Okay? But that's an easy mistake to get confused and make that mistake. Okay, one more question. Find the equation of the line tangent to y equals pi plus x minus sine x when x equals pi. You can go ahead and get started. I'll let you get a head start, but I'm just going to remind you that these ones has to do with using this this formula. Y minus y1 equals mx minus x1. To use that, we need slope and a point. We don't have either of them. We just have the x value. So you got to go find each, whatever order you want. You got to know how to do it. You're getting values for these. You should know that. You're not getting an expression for either of these values, exact values. This is what I have so far. So how to find the slope? Take the derivative, punch your point in to find the slope at that location. Here's my derivative, subbed in pi. What's cosine of pi? Okay. Zach? -1. 1 minus -1 is 2, so our slope is 2. For the point, I sub pi into the equation. So that's pi, which was already in the equation, plus x, which is now pi, minus the sine of pi. What's the sine of pi? Good. So this is just 2 pi. So my point is pi, 2 pi. A little weird, like a little, we haven't seen it before, unfamiliar, but not particularly hard. Probably got those from the graph, probably visualizing the key points of the graph to find those values quickly. Okay. So now we're doing an equation where we are using the point pi, 2 pi, and a slope of 2. So this is y minus 2 pi equals 2 times x minus pi. I got negative 2 pi on both sides, so they're gone. So I've got this equation y equals 2x or 2x minus y equals 0. Any questions? When I was in grade 9, I think it probably happened in grade 9, my teacher said to me, well, the whole class, not just me personally, that standard form, the x coefficient must be positive. Has to. That's how I learned it. And then when I got older, I just realized that that's not true. Like, I think even when I was a teacher, like in my first couple of years, I was probably still under the impression that that was true. That's not really true. That's a textbook thing. Textbooks do that, so it's best if your answer matches a textbook in grade 9. Otherwise, you get confused. Even a flipped negative sign will confuse a grade 9. But it's not a rule. Some places don't get rid of fractions, like some parts of the world, or some disciplines of math. Some parts of the world leave the constant on the other side. So if it wasn't 0, it would be 2x minus y equals 1 or something like that. Like, different places around the world do it slightly differently, and different programs, different software has slightly different conventions and standards. But for us, we use, so I don't care if that's positive or negative, but usually we move everything to one side, set it equal to 0. We still say it's good practice in grade 9 for us to do that. That's what we call standard form, so that's just what we do. Any questions about anything?